So good evening everyone. My name is Ishan Rao and I am a PhD student from Indian Institute of Technology, Tirupati, and this is the fourth live interaction session with respect to the deep learning course. And today we will going to see the implementation mostly with respect to feed forward network. Uh, so one from the perspective of that how we will take a very simple basic feed forward network and we'll try to hand code it, and then after that we will try to scale it with respect to that where we can add any number of hidden layers, any number of uh, neurons within that hidden layer. So that is something we are going to deal with that. So we are going to do that. So before that, to set the context with respect to what we are going to do and all that, we will see its performance comparison with respect to the sigmoid neuron. So we are going to code that as well. So in the first hour, we are going to code sigmoid neuron as well as the uh, basic feed forward network that is hand coded. So Prano just has shared the Google Colab notebook, so you can directly see that also where I'm going to code simultaneously. Okay. So that being said, let's start quickly. So mostly for Sigma neuron, I'm not going to spend time. Mostly I will type it out first, all the code while explaining, and then we will directly see the how it is going to work upon, and followed by we are going to see how it is going to work for feed forward network, how we are improving them. So let me share the entire screen. Okay, now I hope you can see my screen. So let's start with directly so what we are going to do, as a basic outline, what we are going to do today is we first generate a data that is not linearly separable. That is one thing we are going to do, because that is quite much needed to see that how feed forward network can help us to define classes with respect to that. Then we're going to train with sigmoid neuron and see its performance, that we are going to code out right now. First we are going to code sigmoid neuron, then we generate the data, then we will create our first feed forward network from scratch. We're going to hard code it and we see how it can do. Then we will see how it is we can how that this proper feed forward network that first we have created, how it's going to compare with the sigmoid neuron model. Then we going to create a generic class where now instead of writing hand coded, we are going to make it more explicit, more scalable with respect to that, and we're going to train it on binary classification, and then we are going to try on a multi-class classification. And as an output layer, till the binary classification, we are going to use normal sigmoid neuron, but for multi-class, we are going to use softmax as the activation function in the output layer, and we're going to use cost entropy loss at the end. Till before that, we are going to mostly use mean square error. Okay. So this is the outline. With respect to it, there are few setup that we are going to use. So as usual, NumPy, Matplotlib, and we are going to use Matplotlib color. We are going to see where we are using. Pandas is there. Train test split, obviously. From metrics, we are going to use accuracy score, mean square error loss, and log loss. Log loss is basically cross entropy. This is TQDM. It is basically to tell that how much time is left with respect to while training data. You should know how much time is left. For that, it is a kind of indicator. We will see how to use that. So when it comes to multi-class classification for feed-forward network, we will use something called as one hot encoder. We will see that, and to generate random data set, we use make plops, which is our aim is to create a uh, unlinear data kind of thing, which is not linear separable. So we are going to use this thing. Now quickly let me start with creating the class sigmoid, such that because last time we have stopped with respect to theory aspect of sigmoid neuron. So let's just quickly write it down, this code with respect to it. So just a minute. So as we have discussed earlier, or the few of the students who have joined earlier, we follow a certain format with respect to defining any neural any model. So be it MP neuron or this perceptron or sigmoid neuron. So they will be always a init class. They will always be a fit class. They will be always a predict class. So this thing will be common usually, and we are going to restrict with that. Only in addition, we add few other stuff, right? So initialization is usually for the parameters we are going to have. So if you remember, sigmoid usually have sigmoid has usually w and b as parameters, that is we trying to calculate. So it is an exponential function that we are trying to as a sigmoid that we are going to do. Now, a sigmoid function can also be written in two form, that is self. Let me write it down. Now, self is basically a kind of parameter which is tells that whatever variable or whatever object we are going to use is within the class itself. So, self is it's an object of the class itself, and x is the input value that we are getting. Now, a perceptron usually we know that its perceptron function was wx dot uh, wx w dot x plus b. So that is what we are going to do here. So we are performing a dot operation on x and w. W dot t means transposing the w such that they can do the proper dot product, and then that is the basic perceptron we have done. Now if you remember the sigmoid function, so sigmoid function is basically uh, it's upon 1 dot, this is for floating point, 1 by 1 dot 1.0 plus exponential e raised to minus wx plus b. That's how it used to be, right? So wx plus b is something we can directly get from perceptron. What we are just asking, what we are going to do here is wx np dot from numpy. We are going to call a exp function, and we are just putting here, instead of calling a perceptron function, we are just putting it x. Why x? We will let you know, because whatever the value that we are getting here from perceptron is it's going to be stored in x value itself. So when we are going to call the function, you'll understand that why we have put minus x in this picture. But now you can take the statement as like the whatever the x value that we are getting, it's not this x, is basically the returning value of np dot function or the perceptron function. Whatever the value is there, it's going to keep an x, and on that we are going to perform the exponential value. Now once we have created sigmoid function also, now we have to see that we have to update the weights and the bias, that is w and b. So here we are defining four types of grad here. So grad is basically, it's going to tell us that we are going to update the weights, that is delta w that we are going to update for that. Now we are going to update for w, and MSE means mean square error. So I'm going to write the code for both cross entropy and mean square, because we are going to we can use both of these things. And so basic way of finding the grad here is, here we can say we have to find the prediction function. So why we are finding the prediction, why we find the predictor value? Because based on our model, that is the sigmoid function itself, we are going to see that how much we have to calculate the loss basically in this case, right? We have to see that how we can update the weights with respect to that. So now when we are calling here x, so when we are seeing self dot perceptron x, this x that is the input, it is going to call at perceptron, and now this np dot function will going to run, that is wx plus b. It is going to return this value here, and this value again as a x will going to come in sigmoid function, which is we're directly calculating here by putting this x. Okay, so just want to say that this x and this x value will be different when we are calling it as it is. Okay, so just that keep in that mind. And if you have remember the mathematics with respect to it, you might have seen that y cap minus, so calculating a w, delta w, we are going to use y cap minus y, that is here y cap is the predicted value, y pred minus y into y pred into 1 minus y pred into x. So if you're not able to understand this statement, please I will refer you to check the Sigmoid learning algorithm, Sigmoid neuron learning algorithm, where it is showing us how it updates the weight. Okay. Now once we have the same way, we have to write it for b as well. So let me copy the whole code, and so we will put just grad b in this case. The first line will be as it is, that is we are calling for y pred value. Only for updating the b value, we will just remove the into x value from the end. That's the only thing we are going to do that. So it is the by default equation that we got it. Please refer the lectures where they have actually defined it, how we can get the delta w and delta b value to upgrade the weights and the bias. Now this is one way. Now another way of writing, another way if we want to use, just for the sake here, I'm just showing it here, that if we have, here it's for mean square error. So whatever the this written value you're getting, after lot of derivation, partial derivation using Taylor series, you reach to this value. But if you are using loss function as cross entropy, where it is usually a log function, at that point of time, for those for cross entropy, we are going to use log function. So how we can use that? Let me write it down. So again, we are going to call the sigmoid function itself, obviously, as the first point. Let me Control C, Control V. Yeah. So this y pred we will be calling, and so what we are doing is, if y is equal to 0, that is if the actual y is 0 plus, then you have to return y pred into x, and elif if y is equal to 1, then we can say that return minus 1. Here we are not using log function, we are directly using the y pred value. So that's totally fine. Here we can use it, and it has been derived already, so we don't have to look at how it has been derived. So we are assuming on the basis that these equations are pretty much correct, and we are just typing it as it is. Now once we did this, this is for y1 and y class 0. If still the class of y is something else value, might be possibility is still there, so we just raise a error value kind of thing, error message value, which we can write using value error, like y should be 0 or 1. Now this is we have done for w with respect to the upgrading the w value, delta w value, from if you are using a cross entropy loss function. If you do want to do for b, the process will be same, only at the y equal to 0 condition, you have to just return y pred instead of into x, and here also you have to remove the into x value. Okay. Now once we have done with respect to this, now let's get back to so what we have defined as of now, we have defined the model with respect to sigmoid, and then we have defined the updating, how we can update the parameters of w and b. We have written in two different ways, that is using mean square error, and one is cross entropy. C means cross entropy. So just let me, for better understanding, just write mean squared error, and for CE is cross entropy. Okay. Now the main function will come, that is fit. Fit is basically the function where you're actually going to write the main code of the learning algorithm. Okay. So we are going to pass self as an object as it is. We are going to pass the actual input and output vectors in this. Small x is basically one instance of the x, bigger x, or basically the vector. Bigger x contains the whole, all the instances. Similarly for y. Now we have discussed earlier, there are some hyperparameters. So in this case also we are keeping them. because it will become common. So we have epochs and learning rate. We have something keeping as initialize as true. We will discuss what is this initialize. And loss function as of now, uh, assuming that most of the people might know mean square error, will keep it as it is. And display loss is one of the attributes using which we are going to show that how the loss has been decreased over the epochs. Okay, so epoch is one, learning rate is one, initialize we're going to discuss now. So what initialize means, we have to start off any learning algorithm, we have to initialize its parameter, in this case w and b, right? So in this case, what we can do is, if the initialize is true, that is we want to initialize this, sorry, initialize, if this condition is true, then we will give a random first time value to the this weight and the bias. So we can, how we can do is, we can use a random function. So np.random.random, and its range will be from 1 to the number of columns in x. Okay, only with the number of column with x. That's what we are going to see, not the number of instances, the number of columns. 1 means column, 0 means rows. Now self.b is equal to, we are just giving random value as 0. Now based on this initial values, they are going to do all the learning aspects, so which we are going to see now. Also, if we want to display loss, if as the final this thing, so what we're going to do, we are defining a dictionary where for each epoch it will store the what is the loss it is being stored, what is the loss actually happened, taken care by the model. Okay, now that being said, let's start with the main learning algorithm, that is the updating of the weights. Now we are using TQDM notebook with respect to this, and it will just show you a bar. I will show you what TQDM do once we are running this. So let's say, so range we are giving epochs, the number of epochs we want to give, and total is equal to the total number of epochs we want to run, and unit is epoch. So we want, if you want to see that which epoch we are currently in the training model, it is what this is going to explain it out. Okay, so I will explain it. When we are running, you can see it visually properly. So it's mostly for visual aspect. Nothing is this. It's not going to affect any that much in the with respect to machine learning model. Okay, so we initialize dw and db as 0 0, just like what we have done for w and b. The delta w and delta b we are initializing as 0. Now for each x and instance of small instance of x and y, so we are going to using zip function, where small x will belong to big capital X and small y belongs to capital Y. Now just since we are passing function loss function, so we are just also calculating if the loss function is MSE, then dw is equal to self dot grad. Now grad, what is the grad function that we have defined earlier, is we are calling this function, this among these four function, since we are using w, we are calling grad w or grad b for MSE. Similarly for C, we are going to do that. So we are calling grad w MSE, and we are passing both value of x and y. Okay, now similarly for db, we are going to do that. So we will add what based on the whatever the returning value of grad b MSE we are going to get, and update the value of x w and b. Now same thing we have to do for CE as well. So we will just copy this 3 line of code and just make it CE, and you can keep it as LF because any one of them will happen. DW will be calling from grad WCE and grad WCE. See, the reason I'm hard coding this thing is because when actually start using these things, you are not going to see directly, it will calculate automatically. There will be a parameter that you just have to initialize, invoke. All this thing what you are writing here will be taken care by the library itself, like TensorFlow or PyTorch. here just to get, since you might have seen the derivation. So by derivation we are dealing with such cases. Okay, now once our this updating of parameter is happening, what we're going to do is, so for each epoch we are doing this. So what we are doing right now is to we are assigning a value of m, that is basically the number of features we have, and once this w is after one epoch, whatever that value of w is, we have to improve that w with respect to the learning rate. So learning rate, uh, whatever we have defined as a parameter, hyperparameter, we are going to use that, and um, we are going to divide by m. So why? Because learning rate itself might give, sometimes learning rate will be high, but the number of features might be in thousands and all. So if you keep learning rate high, we can divide by m such that the learning will happen slowly rather than the abruptly. Okay, it is an optional thing, but it has been shown that if we divide by the number of features, the learning will be very smooth compared to the earlier smooth, irrespective if we just put learning rate. Okay, so I just do by m and just keep here by b. Okay, so here this 3 lines is basically for updating the weight and bias after each epoch, and we are using m, that's the number of features. So whatever the value of dw and db we are getting at the end of the one epoch, we are just dividing by m, and as usual we are keeping learning rate. It has been shown that learning it improves our learning much better rather than just including learning rate. Okay, now once we have done this, we have updated this aspect as well, and now it's time to display the loss. So how we can show the display loss? So if display loss, which is having we pass as a parameter as true, if that is there, we are going to plot it. So we are use plt.plot. No, before that also, uh, we have to do one more thing. We have to calculate it before plotting, right? So if display loss is there, we have to calculate for each epoch what is the loss. So for do that, we have to assign ypred, and we are going to call uh, the sigmoid function with the updated weighted parameters. Okay, so cell dot sigmoid, cell dot perceptron. Okay, we have already conserved perceptron, perceptron, and we are passing x. So with this weighted new weights and new bias, we are going to again call the ypred, and we are uh, just finding which is the loss function we are using in general. So if it is MSE, then we are just calling loss of I for the particular epoch, whatever the epoch is, and we are calling the mean square error function from sklearn matrix, and we are going to pass y and ypred. Okay, now once this is done, same we have to do for cross entropy as well. So you can play with it once this code is done. After this session, you can apply only C and see what is accuracy and how is the loss has been affected and all. So let me quickly write this. So for cross entropy, we use the function called log loss, and it will compute the differences between y, actual y, and ypred. Okay, now once this is also done, uh, we have calculated the loss for each epoch. Now we have to display it, and we are storing it the loss, which is basically a dictionary. So again we are going to do display loss if this is true, and we are going to plot it. So plt.plot and loss.values. So whatever the values we got for each epoch, we are going to take this, and for x label we are going to write epochs and plt dot y label. So y label, it can be any loss function that we are having. So again let me just take this code, paste it here, and So if loss function is MSE, we just put plt dot y label, sorry, mean squared error, and we just let me copy this line as well. If the loss function is CE, then we are going to put log loss, or in this case let's put cross entropy, because we know this terminology as of now, and we're just going to plot it. So plt dot show. Okay, and the last function that we have to use is predict function, so which is pretty simple. We have to pass the self object, which is by default it will be there, and the input. Now ypred we are putting as a list, and for each instance in X input data set, we are going to calculate small ypred, that is we are just calling sigmoid, and we are going to self dot perceptron into X. Okay, and ypred dot append, whatever the values we are getting, we are just keeping is capital ypred, and we are returning np dot array, which we is putting np dot array, which is a list basically, and converting it to ypred. Okay, so just to summarize, what we have written for the sigmoid function is we have defined an init class where we are initializing w and b by default, that is giving us none. Now sigmoid function is written into divided into two parts, that is sigmoid and perceptron, where perceptron is wx plus b, and if you remember in sigmoid function also we have 1 divided by 1 plus e raised to minus wx plus b, so that wx plus b we are calculating using perceptron. Now we have we can update the value using two ways, that is say updating the value depends on the loss function you are using. So here we are updating w and b using two methods, that is mean square error and one is cross entropy. Now once which is usually done by automatically, here we have hard coded it. Now in the fit function, which is a basically true loss function, here we are initializing w and b randomly, b as 0 and w as some random set of weights, and we are created a loss dictionary where for each epoch we are going to store the loss value of the model. Now this is basically the learning algorithm, where for if you have a loss function as MSE, so you are going to see that at what is the w and weight w and b, how we can increase it, update the value of that we are going to do. And once we have model has been trained for one epoch, we are going to ask for the sigmoid loss with the updated w and b, and we are going to store that in the loss dictionary that we have defined earlier, and this is the code for plotting it. Okay, and this function is basically of prediction. Okay, now that being said, this is the first thing we have done. Let me add few more thing here, such that we can see it properly, because we have just wrote the sigmoid function and we have done anything else as per now. So we have earlier, if you have seen in the library that we have defined, there's something called matlab.colors. Now why this is there, you will understand it now. Basically it's for illustration, to show you that the data we are going to generate, it is for multiple class. So to get a better understanding, we are just defining a customized colors and all that, in which color they should show. It is a this is something for visualization only. You can skip it if you not need to understand. That is totally fine. Okay, now to generate a random data, and which should be non-linearly separable, what we can do is so we can use the function called make blobs. So make blobs, and let me write this thing. So and make blobs has attributes as number of samples, centers, which is basically tell the number of clusters we want to make, that is number of different type of data we want to have, number of features per data, and the random state for the reproducibility aspect. Okay, so if you keep at 0, So whatever I am writing right now, you can also reproduce it when you're trying to do it in your system. Okay, so labels dot shape. Okay, so what we are doing when we are making make blobs, we are doing 100,000 samples randomly for 4 clusters, and it has 2 features. Okay, now it will come into data aspect. Now labels will give us the 4 clusters, so it might be a 0, 1, 2, 4. This 1, 2, 4 will be assigned in this label. Okay, so if we are going to run this make blobs. Um, Okay, I haven't. Okay, let me run this setup first. Now, yeah. Okay, so what we can do is we have 100 instances, 100 points with 2 features each. That's why it is there. Okay, so that's why 1000 we can't have 4 columns. Now to see visualize the data, what exactly data on which we are going to work upon, the data we have created. So I'm going to use the plot.scatter function where the x-axis will be, we can define it from the data 0 from their data, and to show the y-axis we can write it like this on colon comma 1. So x-axis y-axis are similar. Now c is equal to the number of labels that we want to have. The c is basically color, so the number of labels we have, in this case 4 different type of labels that is going to have, and this is a customized function that we have wrote earlier in the above cell, where is defining us a coloring preference in the plot. Okay. Okay, I haven't done one thing. I have to do plot.show. Yeah, I have to do this. Okay, so yeah, so now you can see that this is a random point that it is generated. It has 4 different classes: green, light green, red, and orange. Orange or yellow according to your screen. So that is there. Now we want to work basically on the first. We're going to work on this as a feed forward network. So what we want is that we want to define a function, customized function using feed forward network, such that the green should come into one class, lapping is happening, and you can't just put a one line, you have to put multiple lines here, right? So how we can do that we will see, but first before that we want to see that whether Sigmoid neuron take um, can do something about it or not. So instead of giving directly this 4 cluster, we're going to make it as a binary class. So what we can do is we just going to see, as instead of 4 class we can have 2 classes. So to do that, so I'm just putting original labels into labels underscore org, and the labels I'm going to do certain kind of operation. So if I write np mod 2 on the labels or org, I am dividing by 2. So what is happening? So if I remember how you take a odd and even, so odd and even, to identify number is odd or even or not, you just divide by 2. So similarly what they are doing here is for all the labels, even though we have 4 labels here, we are going to divide by 2 using np mod function, and we are going to put every function into either 0 or 1. Okay, now to see that how the data looks like now, let's see here. Um, okay, sum is something. Okay, I haven't run this. Now I should run this. Okay, now we have earlier 4 clusters. Now we have divided into 2 clusters. As you can see, this is also, it's not a linearly separable data. It is a non-linear function. That means somehow we have the model has to, or Sigmoid neuron has to find some way to classify this red into one class and green, which is in 2 different spaces, as a different class. Okay, so let's see how we can do that. So we will try to do basic sigmoid neuron classification, binary classification. So let's train it. So now earlier we used to write x train and x test, but testing, as we know, testing is for different purpose. So we are going to use only the validation aspect as of now. Okay. You can use test also according to your needs, but right now for the sake we are going to use validation. So we are going to passing the data, label is either red or green, and stratify we are using it for so have a proper ratios, that is number of red and green points in training, the ratio should be maintained in the validation set also. For that we are using stratify, which we are doing according to the labels, and we are doing random state equal to 0, that is for reproducibility aspect, and we are just printing it uh, xtrain dot shape and xval dot shape. Okay, now if we are going to run this, now we have two classes, 750, that is a training with two labels, and 250 as a validation with the two labels. Now to run this, let's define sigmoid neuron as a object, Sn is the object of sigmoid neuron class, and we're just going to put fit function. So we're going to pass xtrain, ytrain, that is the actual output, the number of epochs, which is going to be 1000, learning rate is equal to 0.5, assuming left one we can change it, you can play with that, and we're going to say the display loss, that is we're going to see that how the loss has been loss function is dealing with when the model has been trained over 100 epochs, 1000 epochs. So let's run this. Okay, unexpected learning keyword. Okay, let's see. I have this as learning rate. Okay. Okay, so it will take some time with respect to this, maybe a few seconds here. So we will see that how loss function is there. So in the meantime, let me check if they have any questions as of now. And call messages. Yeah, now TQDM notebook. Now the TQDM notebook is basically, now what you're seeing is here, if you can see I'm highlighting it, right? So you can see that how, what is the progress, how much happening, in which epoch right now you are in, how much the total number of epochs are there, how many epochs per second is happening, and how much time is left, right? This thing you're going to get it using TDM notebook. That is for this, for I in TQDM notebook, ranges epoch, that is number of times this has to run the for loop, the total epoch, that is 1000, this is 1000 you're getting here where I'm highlighting, and the unit of each total number is 1 epoch, right? So that is, it's showing that how many epochs per second it's happening. Okay, now if you can, if you have understand this TQDM is basically for visualization, because sometimes you're going to run the code and the model is going to run for hours and hours, so you don't know how much time will it take. But if you use TQDM, you will understand that okay, this much hour it might take. Okay, it will give a very approximate estimation, not exact, but it gives very good enough estimation with respect to it. Okay, now what we have seen is they have done, it has done some work. So from loss from zero point 0.7 it is going down here to approx 0.31 kind of like that. So if we and since you can see there's a lot of up and down kind of things there, that means if we increase the learning rate we can make it more smooth. But right now since it is taking time, let's keep it learning rate 0.5 and go ahead with respect to the testing phase. So what we can do is ypred train sn dot predict xtrain, sorry, the testing phase of it. So that is one thing. So ypred train is there, and now usually if you remember the sigmoid neuron, what sigmoid neuron do is actually it is giving a probability value between 0 and 1. It is not exactly giving us whether it's belong to class 0 or class 1, right? So what we can do, what we have to do is whatever the output final output we are getting, so we have to convert it to either 0 or 1. So how we can do that? By putting a threshold. So any ypred train value which is greater than equal to 0.5 we are putting as class 1, otherwise class 0. Okay, so this is for training. Same for validation also we will do. So how it will run on validation data. So let me change few things, xpred val and xval. So binarization train is basically, you just need to understand that the sigmoid neuron will never give class 0 or 1. It will only give value as uh, some 0.23, 0.78, kind of like that. So we need to assign it to 0 or 1 class. So if threshold is greater than 0.5, it is class as 1, otherwise class 0. Okay, so using this code we can write it down, and if we want to see what is the accuracy of training, uh, we can directly use sklearn matrix score, that is accuracy score by pred um, binarized train and y train. So we are getting the predicted value and the actual value. This is the one thing, and let me copy this line again. We have to do for this also. Val accuracy score will be by pred binarized val and by val. Now once we get this value, we just need to print these things. So let me say training accuracy. So whatever the value accuracy will be, it might be in floating points. So we're just keeping the values within the 2 decimal points. So we just use accuracy train 2. 2 means whatever the value will be there, it will come down to point decimal 2. Now for this is for training and this is for validation. Okay, now this is accuracy val. Okay, so if we're going to run this code also, it is giving a very less value, let's say 0.7 kind of value. So if we improve the learning rate, we might get better results as well. Epochs is already high, so we don't need to do that much of uh, training with respect to it. Now let's try to plot this data again. So let me take this code as it is. So let's see that how the training is trained model is doing this. So obviously X is so instead of data here, we're going to put X train, X axis instances, X train Y axis, and C will be, since we have only 2 labels because we are doing binary classification, so it's Y binarized train. Okay, C map is my C map, and I will tell you one more thing which I am going to do. So let me write this code. This is for visualization purpose. It's not something we typically use. It's basically for our understanding of the data. So what we are doing is np dot absolute value. We're finding the absolute value of binarized train minus y train plus 0.2. Okay, so what this component will do is it will identify those points which are actually very longly classified or kind of like that. Okay, so that means the smaller point, now you can see that earlier our data was like this, it's by red was in middle and green was in the either side, but what sigmoid neuron has done is it actually crossed a line and it divided the middle line, that is red and green red into red and green. Actually it should be red only, right? Now why I have done this s equal to 15 dot m np absolute and all, basic reason is to see, to tell you that which one has a more loss or which has been more wrongly classified. So the bigger the points you can see, that means that they are not properly able to classified by the model, and the smaller ones are properly classified. Now how we can validate it, if you can see here, this the middle part where it has been red and green both, you can see the number of green points are very large, very the size of that points are very high. So it tells that these points are wrongly not they are very the way it's classified is actually it's very far away from the actual class. So that's why it is giving green. Similarly for red points also, the red points actually should be green, but it has given very high size or big size of the points. So it is telling us that these bigger points of either red and green, they're actually very far away from their actual class defined. This is for the demonstration purpose, because either by this way you can understand that okay, it has wrongly classified, Sigmoid has wrongly classified the red and green dots, but the size of the dots will also tell us that from where actually it has been wrongly classified. Okay, so green it's on the right side and red on the left sides, it has been wrongly classified. So that is what that is what we're going to, the sigma neuron is able to do with the accuracy of 0.68, or you can say 0.7 if you round it up, right? 70% accuracy. Now okay, so let's before going to random feed forward network, the basic simple feed forward network, let's see the questions. So okay, so its question is, it's okay up to the predict function. After that I can understand the code because there are many unknown libraries function. Do we need to learn all this for the exam? No, mostly, see again, uh, by the time we are going to use another 2 months, even you don't need to write this course also. If you're going to write, that is still good, but all this thing will come down into one single line, because all this thing that we are defining here are all going to be written in a single line or by a TensorFlow or PyTorch. Why you need is to get a better understanding about how the mathematical derivation that you got for the learning algorithm, how you can write it as a code. Okay, more sense will be look when we're going to see that the feed forward network as well. So you don't have to remember it, but practice it such that you can get understanding. Another important thing is, for if you're asking with respect to PLT data, that is the plotting thing, you should practice a lot. The reason being, you have to see that how your model is performing. Just by number you can't understand it, so you have to visualize it. So plotting, you have to start keeping learning out the whatever the matplotlib, how it can function, what is the various way you can show your outputs with respect to the actual data input you have given. Okay, so many unload libraries are there, but these are quite commonly used libraries. So like train test split is a very commonly used library with respect to that, so the parameters are very commonly used. Make blobs are one also very commonly used data, because every time they might not say that use a proper data set available, so they might say to create your own data set. So make blob is one such function which can help you to create your own data set randomly. Okay, so that is one thing that you need to take care with respect to it. um, so these are very common one, so keep checking as of now, because whatever we're going to see, the mathematical equations and all, that is you can skip obviously, but what you don't need to skip the procedure. So sn dot predict, you have to you're predicting for a exchange, so you have to define a wide prediction train, kind of like that. So there are certain terminologies that I'm using, so please keep that also in mind, because these are predominantly used in the machine learning aspect as well. Okay, okay, so before taking break, let me just uh, define what we're going to do next. We're going to hard code a feed forward network, and why it is called feed forward network, what we're going to do, just let me uh, define it properly before um, okay, can I, no, I need to minimize it a lot. Okay, I think this is the max I can do. Okay, that's fine. We will deal with this. So this is a very basic feed forward network with only 3 neurons. Oh, okay. Now it has been done like this. Just a minute. Let me deal with the zoom first. I think it's taking a lot of time. Let me keep it 50. Let's see what will happen. Okay, I think this is fine for explanation as of now. Yeah, everything is seen on one screen. Okay, so what we are going to do is, 3 neurons are there. We have only 2 inputs, x1 and x2, and we have one output y. Okay. Now what we have to do is, this simple feed forward network, we are going to hard code it properly, and then after that we are going to code for a much larger scale where you can define number of layers, number of neurons with respect to that. So before, okay, so we're developing on top of sigmoid neuron only, we are not defining any new neuron. So this sigmoid neurons are there. Okay, if this part is clear, now let's go to the internal part of it. So we have x1 x2 as in input layer, uh, let's say neuron 1 and 2 as hidden layer. There's only one hidden layer with two neurons, two sigmoid neurons, and the output layer consists of one sigmoid neuron. Okay, now each neuron will be passed will have its each neuron will get both the inputs, that is x1 and x2, and each neuron will have a bias. So in this case x1 for h1 and a1, which we can see, I will tell you what are those. So x1 is giving to the h1 a1 neuron, which is w1. x2 is giving it's with the w2 weight to the this neuron, and b1 is, this is what we are going to give as an input. That is usually how we do. We initialize certain random weights here. So b1, w1, w2 will be mostly randomized weights. So based on this value, I'm going to go for w5. Similarly, for h2a2 neuron, we're going to pass w3 x1, x1 as a with the weights of w3, and x2 with the weights of w4, and it has its, each neuron has its own bias. So here the b2 is the bias. Okay, now this once is done, now let's try to understand what is h and a. Okay, so there's something called as pre-activation and activation function. Here a is basically the activation function, h is basically see, a is the pre-activation function, h is the activation function. So since the first layer, input layer, is going to here, basically the wx plus b, the simple basic perceptron model that we have seen, that is going to calculate. After this, it is going, based on the value of a1, it is going to calculate the sigmoid neuron. So what is the value of a1 you get, you're going to put that in sigmoid neuron function model and going to predict the value. Okay, so that will be the new value of the this particular neuron. Similarly for a2, so you will write w3 into x1 and w4 into x2 plus b, that will give you a2, that is the pre-activation, and h2, which is a sigmoid neuron function, is going to take a2 as an input and going to find the value here. Now once you get some value, let's say some value here, then from here this you have to go back to the next layer, that is forward, you have to forward it, right? That is a feed forward. So now you have to go to the next neuron, which is in this case the output layer. Now to give a3, what we're going to take, whatever value we have calculated here from using the sigmoid function h1 into w5, whatever calculate we function for neuron 2, h2 into w6 plus b3, that will be a pre-activation function, and h3, since it's a simple neuron we are taking, here we are taking it as a simple sigmoid function, it will take a3 as an input and it will calculate the y value. Okay, so this is simple feed forward network that we are going to hard code it as of now. After that, what we are going to do is we are going to create a proper generalized generic feed forward network where we can have n number of input in features in input layer, n number of hidden layers, and in each of the hidden layers we can have m number of neurons. That is what we can going to define. Okay, so let's if you have any question, please let me know in the chat section, and maybe by 7 o'clock we will start again and we will hard code this model that you can see on the screen. So whatever this we have I have taken this image from a source from where we are going to exactly write this code here. Okay, so if you have question, please let me know, otherwise at 7 o'clock we will start again the coding part. Okay. Yeah. Uh, so actually, okay, so the number of libraries that you're going to see here is maybe initially the starting phase you can see a lot of libraries, but this sum of the libraries is going to repeat again and again, and so you don't have to worry about that. What you have to do is little bit practice with respect to it. So practice as in whatever the code that we are right now writing right here with respect to it, you try to connect with the theory, okay, and just manually write it again and again. Okay, so that is what you have to do with respect to it, and as you start doing it, there will be few other questions, this exercises will come where you have to start developing it. At that point of time, again you can refer back here. So visualization is basically very good practice that you need to learn to make some other person understand the data as well. Okay, so it's not only limited because accuracy will give. Do we get codes in the exam? Maybe you can get codes in the exam. Mostly I haven't seen that earlier also, so I can't actually comment with respect to that. But since at the end of the day you have to develop it, you have to code it here, so practically you have to see, you have to write the code, right? At the end of the theory will get you to a certain extent unless until you make it right in a proper, you have to make, you're going to make, if you're going to industry you have to deploy it properly, right? So visualization will give you a much better understanding with respect to that. At the exam, I think they might give small code snippet. They might not ask you to write this big code. And whatever the code we are writing as of now is basically for understanding of whatever the derivation you have got here. We are just directly copying it and writing it here. It's not something we are defining from our own, right? So maybe in one of the sessions, once we get more comfortable, maybe after 3-4 weeks, we can write all these functions, maybe from NP neuron to perceptron, Sigmoid neuron, feed forward network, back propagation, feed forward network with back propagation and all. We will write all this code with one single line. Okay, but before that, to get to that stage, you should know that how you can, yes, first you should know how you can try to make this thing work. Okay. Okay, so that being said, let's start with the feed forward network. uh, Unpin myself. Okay, awesome. um, I hope you can see the screen here. I think night mode has been on already. Okay, so let me zoom in, and 125 is fine. Yeah. Okay, now what we're going to do is, as we have seen the earlier, the simple three neuron feed forward network, we are going to deal with that. Okay, now let's see. So let's start writing code here. So so what are the parameters here? So we have, let's start with that, because eventually we have to deal with what the number of parameters we have to learn. So we can see that for each neuron we are passing one weight from the x1. Okay, similarly from x2 as well. So here we have uh, four weight vectors, and from each neuron we are going to pass another weight to the final neuron. So we have 5 and 6. So total we have 6 weight vectors, and for each neuron there will be one bias. So one b1, b2, b3. So they are total 3 bias. So in total we have 6 weight vectors plus 3 bias, total 9 parameters. That is something we need to initialize. Okay, so let's be same. So class will be, let's say, first ff network. Okay, class name. The first thing you're going to do is initialize your parameters. In this case you have 9 parameters, so let's write it down. So we have w1, and you're just randomly initializing it. So we can do that np.random.randn. Okay, so similarly we have to do for another 6 weights as well. So let me copy paste these lines. 1 2 3 4 5 6. Okay, I will just use for b1 as well. So for w2, w3, so we are finally going to do for random weights. Okay, now we have b1, b2, b3, and for b1, b2, b3, for since we are initializing like this, just keep it as 0. So this is the first thing we do. We initialize the weight and the biases. So once this is done, now let's define a sigmoid function as well. So the sigmoid function will be here is, we can directly take it from the sigmoid function that we have taken from where I have written class here. So perceptron and sigmoid, that is something we needed. We're going to take it from here, and okay. Why sigmoid functions we are again taking? Because these neurons are basically sigmoid neurons. When we say, now we are trying to create a network. This is basically a first deep neural network for you people coding it out, right? And that is built, the basic block of that network is a one sigmoid neuron, right? In this case we have 3 neurons. So we have perceptron and all this stuff. Now the main thing will come, 2 main things are required for us. So the one is forward pass, that is from x1 and x2 how we reach to the this first 2 neurons. Okay, this is the first forward pass. That's the one major important. Another important part is how we update the weights here, that is w1, w2, w3, w4, w5, w6 and b1, b2, b3, how we updates those weight. Okay, so that is one thing. So we're going to define a forward pass here. That's the one important function. And another important function is grad. Grad is basically update the weights of w and b. So here instead of passing capital X and Y, we are going to instance of X and Y. Okay, for forward pass we are just going to pass the input instance. Now for forward pass, what it will do is, considering now we are going to use the same data. Okay, so data that we are looking here, this data that we have seen, so it has 2 features, x, maybe considering it's a 2D plane, so let's assume it has x and y, x1 and x2 as a coordinates, right? So that coordinate we are going to see here. So for each input instance we going to extract x1 and x2 from the input x. Okay, now to define a1, basically what we are doing is a1, what we are going to do basically a wx plus b kind of scenario, that is w1.x1 w2.x2 plus b1, right? This is what we are, this is a basic wx plus b. We are going to for a pre-activation function. So let me write it as a pre-activation function here. So this is called pre-activation function. So A is belong to pre-activation function as a terminology, and H is activation function. So how we can write it down as w self.w1 self.x1 and self.w2 into self.x2 plus self.b1. Okay, so this is the pre-activation function. Now once we get this, now we have to find the activation function. Now activation function is basically a simple, since it's a sigmoid neuron, we are going to apply the sigmoid neuron as well. So for self.h1 we're going to write it as self dot sigmoid. We're going to call sigmoid function. I'm going to pass self dot ai, not ai, a1. Okay, so whatever the value we calculated here as pre-activation function, we're going to call it, and because of this we're going to find the value of h1. So that is what we are trying to do. Similarly, let's copy it for other 2 times as well. Because we have 3 neurons, so we have to define it for 3 times. So sorry, h1. Now pre-activation for a2. Now what we're going to find for 8, that is for second input feature, w3 dot x2 and w4 dot x2. Okay, and sorry, here it is x1 itself, and self dot b2. And activation function is self dot h2, and it is going to be what is the value of a2 what we got. We are going to pass as an input to the sigmoid function. Okay, now once we have this, similarly for the last input a3, so we are going to pass h1 as our input, h1 into w5, h2 into w6 plus b3, right? So that is we're going to put. So let's write it here. So a3 will be w5 into self h1 and w6 into self h2, that is neuron, the output from the second neuron from the activation function, and we're going to define the bias of the last output layer. Now output layer will come down to a3, and the final output we're going to get it from h3. What is the activation function we're getting sigmoid? We're going to find it from here, and later we're going to just want to return this output of h3, which is which is going to be between 0 and 1, because sigmoid returns value between 0 and 1. Okay, now once don't worry, this code will not be there in exam. It is mostly for you to understand that how you can develop a code, because in exam it might not be there, but eventually you have to code it out eventually at some point of time. If you're going to pursue deep learning as a career, as a researcher or as a practitioner, you have to write all of this code. Okay, and just we are just trying to, before using the basic functions directly, what we are aiming for is to dissect it such that you should know that how you can, whatever the mathematical equation that you have seen, so many mathematical equations in the lecture, how you can codify it. It's not that much different. Okay, now the next part is the importance of grad function, that is how to update the weights. We have 9 parameters, we have to update the weights. So how we can do that? So there's a particular function here, particular equation that we have to use. So let me write it down. If you're not able to understand this part, that is totally fine. The crux is here is to understand that the derivation that you have got, the same thing we are going to use as library at the backend. This will the code, this kind of code you will be mostly seen. Okay, so self.h3 and self.w5, then self.h1 into 1 minus self.h1 into self.x1. Okay, so it's a very big equation for updating a weight vector 1, where it is taking the output function, that is a predicted output. Self.h is the predicted output minus y, and the predicted output again into 1 minus predicted output again. Then this a weight 5 vector is come into picture. It's all comes to derivation. It's not something I'm deriving it. It's a basically coming down to equations. So let's we can just skip it quickly. Just let me write the whole function, because eventually we are going to use this at some during our model training, and we will see mostly during the model training what we need to do. So h3y will be same as it is, h3 will be as same as it is, w5 h1 1 minus h1. Here x2 will come into picture. Here this thing will be okay. So it's basically coming from the gradient function that you have, how we can define the w and b1. Now same thing we have to define for two other functions different times as well. So this is for weight vector 3, weight vector 4 and the bias 2, and we have to define for weight vector 5, weight vector 6 and bias 3. You don't have to remember this, eventually again tell you, just for our understanding we are doing this properly. Now S3 into Y, and same W5 will be here. Now here W6 weight vector will come into picture. So let me do weight vector as this, and H1 will be same as it is, X1, X2, and here weight vectors will be in W5, W6 weight vectors, HCH is there, and here you just need H1 and H2, and rest of the things will be removed. So let me remove this, and even this part will not be available for this. Okay, so this is a kind of updating function that we have used. This is coming from proper derivation, that is totally fine. We can skip off to understand this part, that you just assume that weight vectors has been updating based on the predicted value of y. If that you can understand that, that is more than enough. Now we have to write the fit function, which basically a learning algorithm. We are going to pass x and y as input and output, number of epochs we want, learning rate we want, and we want to a function called parameter called initialize, whether we want to initialize certain weights or biases or not, and whether you want to display loss or not. Okay, these are the common parameters you can find even in TensorFlow as well. So there's nothing new that we are defining here. Initialize W and B. Now once we have this, let's initialize W and B properly. If this is true, let me copy the paste from above itself. The same thing how we initialized earlier, same thing we are going to initialize here as well. So yeah, now if you want to display loss for each epoch, and loss is equal to this is a dictionary we are finding, and let me copy some code from above for TQDM part, so that I don't need to write it again and again. Let me copy this here. Okay, so TQDM, this for the bar that you have seen, the time, about the number of time it will take to your model to train, right? For that we are doing this, and now we are going to initialize the delta W1, W2, W3. Till now we have defined the weight vectors, but not the delta one. So we are defining it right now. DW5, DW6, and DB1, DB2, and DB3. These are delta biases and delta vectors. So we are just assigning them a value of 0, and so for each instance of x and y from the input capital X and Y, once we do this, we're going to call the self grad dot x and y. So from the graded function x and y we are going to call, and we're going to update the values accordingly. So w1 is equal to self dot w1. Now let me copy this thing. 1, 2, 3, 4, 5, 6. Okay, let me change these values. So any whatever the updating parameters, we have defined the grad function. So we have already did that. 4, 5, 6, db1, So that's how we are updating the weights of delta W and delta for weight vectors and the biases. Now once we did that, okay, now once we do this, only thing we have to update the actual weight after each epoch. So this is what we are updating is for one epoch, right? So we can define dot x equal to x dot shape, same logic that we have done for sigmoid neuron. Just keep a smooth learning rate. We are updating the parameters very slowly. So here we are using the meaning of learning rate properly, and dw by m says that the weights will update very slowly says that learning will remain smooth. Now let me do it for okay. So w2, just bear with me for 2 minutes here. Let me complete this code. Then we can do proper analysis. What are the things that you need to play on with, that as exercise you can take off at the home. So w5, w6, w7, b1, b2. So that's how we are updating the weights as well. Now once we do this, I just need to basically display the loss. First, before display the loss, I need to calculate the loss as well for each epoch, and I have to store it in the loss dictionary. If display loss is true, then y predict and call the predict function, keep it value x, and here for the sake we are not using cross entropy now right now because of binary classification. For me, for multi-class classification, we are going to use that part for sure. So y pred y, and okay, now if I just need to plot it, for plotting I will use for if display loss plt dot plot loss values. So for each value will be displayed, and where the x uh, axis will be the number of epochs, and y labels. So it's label only. Y label will be mean square error. So whatever the loss for each epoch that we have found, we are going to put it, and just finally we're going to put show. We're just going to call it. Only final thing remaining is prediction. So predict self x and y pred equal to this for x in capital X, y pred is equal to self dot forward pass, and so y forward pass instead of predict is because uh, here in this case we are passing through the 3 neurons that we have defined properly, right? So that's why we are calling the forward pass here the way we want our data to flow. That flow is we are telling it as a prediction. Okay, so we have written a very big code here. Let's run this and use it for classification. Okay, so let me define our object called ffn, that is first ff network. I'm creating an object of that, and I'm calling from that object ffn.fit, and I'm passing x train, y train, epochs. Let's keep 2000 because we haven't get proper accuracy at that point of time. So learning rate, we are keeping it little less, so let's say 0.01, and we are going to display the loss. Okay, so let's see if it's everything running fine. Some error is coming. Okay, something is there in grad function. Okay, I need to do this as self-fetch too. Okay, this has been done, and anything else I need to check here. H2 will come into picture again. W6, H3, H3 is there as it is. X1 and X2 is there. DB2 is there. Okay, let me run this code again. And let me run this code again. Again some value. NumPy float object is there. It's not callable. So W1 is NumPy. Okay, so fit train is going to forward pass. After forward pass, it's going to this. Okay, it is going for W1 itself. Let me see what is W1 I'm trying to do here. So forward pass X is going as it is. Self H3 is there. Okay. Self H3 is fine. Minus I is fine. This one, just give me a minute. I'm trying to understand where I'm falling it off. Forward pass. Let me check the forward pass also. Some problem with forward pass. X1, X2 have defined. A1, WX1 is there. There's no transformation. W2, X2, B1. A2 will be W3, X1, W4, X2, B2, sigmoid. This part is correct. I don't need this as of now. Let's keep it. Okay. Still I'm getting some error. Same error. Okay, here I'm getting okay, W3. Okay, anything else where I'm getting some error? Grad. No, same error. Okay, I think I have to fix this code. I'm not able to identify where is the problem actually lies in. Why the numpy 64 is coming into picture here. Grad function is usually it is simple code that we have written. W5, W5, W6, W5, W5, H3, 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 1 minus H3, H3 minus Y, and self X1. This is the problem. I haven't put the multiplication sign here. Okay, I think now it should work. Okay, now DB3 has issue where it is. Oh my god. Okay. DB3. DB3, why I put DB3 here? This is the problem I got again. Again some issue. Too many values expected from X. Too many values to unpack. Okay. So let me run this code again maybe. Let me go again. Because I am passing X train itself. So let me go to the X train itself where I am finding it. So this is the data I'm trying to create, and this is the label I'm trying to generate. This is how we have 1 0, and we're finding x train value. Okay, now we have this. Let's go here again. Okay, so if you write very big code, you're bound to get a lot of errors. x1 and x2, again some problem. X is not coming properly. Okay, where I am falling properly, where I am getting wrong. X train, y train. I'm calling the fit function. Let's go to fit function here. Fit function. We are finding x and y properly. Epoch is there. Okay. Now from here we are going to the forward pass. Grad. From grad we are going to forward pass. Grad we are okay. From grad we are finding x and y, and from y x we are finding the x here again. Self x is there, and this is the x1 and x2. Code seems to be okay. So where I am getting wrong? Okay, let me see again. X and y is there. I'm calling grad and x and y. So it's from here the actual code starts. X and y. Grad x and y is there. Then from there we are going to grad function, and we are falling for forward pass x. Okay, let me see understanding the what is the x train here, so that I can get better understanding. So I just need to print x train dot shape. So it has two variables only. So this is typically fine. So we have two variables. So I don't have problem from here. Then where I should go? Here. Before calling x and y, let me print the can I print the shape of x and y here? Let's see. Here I need to print, and I have to print it somewhere else. Forward pass. So print x dot shape. Let's run this code. I hope I should not get new errors. Okay, so I'm getting two values only. So two values is perfectly fine. It is giving me proper value answers only, but why it's not able to unpack in that case? Okay. Okay, so where the problem actually lies here is x has 2 points, x1 and x2, but it's not able to assign it here. So I'm trying to understand why it is not able to assign it here. Even though x values are perfectly fine. Here self x1 or self x2 comma self dot x2 is equal to x. This is what it's not happening. Okay. Sorry, I'm taking a little bit time of your time here just to figure it out where the actual debugging problem is with respect to the code. Self.x1 is there, self.x2 is there. Let me give me one more time. If not there, then I will put the proper code. I will open it some code here, and then I will try to do that. The question is too much to unpack. Too many values expected to. How many values do they want? Okay, do you have any solutions? Let me check. Okay, okay, why is the same problem is coming? Okay, fine. What I can do here is maybe I will open the notebook page where I have tried, and maybe I can show it properly better there, because that there the code is running. So let me open that code. Let me change it here, and till the time it opens, let me again figure out cell dot access there. X1, X2 is there. It is totally fine. Okay, I am making some mistake, but I am not able to understand where I am doing exactly. So let me take the code directly from here. I'm just going to copy the whole code that we have written here and exactly in this, because usually it should work. Let me run this, and let me run this as well. Now it will take some time. Okay, so till the time it is there, I need to understand, because as far as I know, there's no problem with this line of code where it is actually showing error. So maybe I will see what is the problem, and I will try to give you better explanation with respect to that later. Okay, now what we're doing is we have created the feed forward network, the same thing that the image simple 3 neuron feed forward network that we have shown, with 6 weights and 3 biases, and with pre-activation and the activation functions, 3 pre-activation and 3 activation functions. We are trying to fit the data. Okay, and then the data that we are trying to fit here is this kind of data. Um, this data, where we want to predict red points as it is and the green points side by side, and we want to see whether these 3 neurons can able to help us in that or not. Okay, so what it is showing is, it is showing pretty good loss after certain time. After 2000 loss, it have certain in between, there's some problem with respect to it, but after that it is reducing properly to less than 0.05. So that means it is giving us pretty much good loss, pretty much good learning with respect to it. So let me see what is the training and validation accuracy. For that, let me copy the code from above. We're just going to change it here, and after that we will just, once we see how it is going to play, then we will play with this model for certain time. Okay, so ypred train is there, and then instead of sn I need to call ffn x train ypred. Again we have to pick binarized train. The reason is simple, uh, because we have only want to define 2 classes. Similarly, instead of ypred val, we go to ffn n dot predict, and okay, I think pretty much everything is good. Let me run this. Okay, so it is giving us pretty good accuracy with respect to that. Now let's see what exactly, whether it is actually able to divide the data points into its own way or not. Instead of getting this, which is we got from Sigmoid neuron, we will try to see from feed forward network, a simple feed forward network, not the complex one as well. So let's see. Okay, so it has done pretty good job with this, because as we have seen, the accuracy is pretty equivalent to 100%. So it is able to identify majority of the points as it is, as we have found in the original data, right? The red in the middle and green by side. What also we can see here is there are some big points, which actually are supposed to be green, but they are showing as red, and the big green dots were supposed to be red but showing as a green point, right? So it has done pretty good job with respect to it, and you can try to think like that, like one sigmoid neuron is able to give us this type of classification, But if we add three sigmoid neurons in a particular order, which is basically feed forward network, it's able to capture a pretty good amount. The way it is doing it's pretty good. So to understand more and to try it out more for you people, what you have to do is you have to play with the number of epochs or the number of neurons. Okay, so first let's say if we reduce the neuron number of epochs and learning rate to I increase the learning rate, what will happen? Okay, uh, so I'm just reduce the epochs and all. So as we have seen for 200 epochs and learning rate of 0.01, it is given us pretty good value. But if we reduce the epochs and learning rate, how it is going to affect us? Okay, so it is done. Now you can see that how the loss function has been varying. It went down to 0.05 to a certain extent, again come back and maintain between 0.15 and 0.20. So we can see that the number of epochs, since a non-linear function, even though the loss is less, but not as less as the previous one, and the training accuracy has been reduced to 0.73. Okay, and if you plot it, it's somehow acting as a sigmoid function as well. It's not able to, because if you can see the big red dots here, it's supposed to be green but it's showing as red, so that means it is somehow the, even you have more number of neurons also with less epochs, you might still the network will act as a typical sigmoid function, right? So let's do one more thing. Let's increase the epoch uh, and keep the learning rate as earlier, that's 0.01. That means we're only increasing the epoch. So is it going to help us to any extent or not? It will take some time. uh, so Balaganesh has given me the answer where it is, it should be not, it's not writing properly. Okay, I will check that code as well properly, and then I will edit it. But for now, let's keep up with whatever the code we have written right now. So it will take some time. So as the number of but we have to now have to understand that if we increase the number of epochs, because we should not get into this habit where we will think that increasing the number of epochs or the learning rate, decreasing learning rate will improve our learning all the time. Because for example, for 2000 epochs, my model is trained, maybe took 30 seconds. Now it is taking almost 1 minute with respect to it. And if it's not improving my accuracy that to that extent, there's no point for me to continue the increase the number of epochs, right? So it is, as interestingly we can see here that it has done pretty bad job with this. Earlier it was 0.05, now it is become 0.18, and if we try to run it, the accuracy has not actually that has been improved. And if we, let's see this, okay, it's showing something as it is. So let me, what I should do is let me rerun this again. I think some flaw with the code as well, because showing even for 3000 epochs it's showing the same data. So let it run one more time. It may take a minute. Okay, so what your exercise should be when you're going today is basically to understand that what is the relationship between epochs and learning rate with respect to any neural network, any neural network. Okay, so in this case, feed forward neural network, we might assume having higher epochs learning rate might give us better accuracy, but it will stop at certain point of time. It will not increase. It will increase in within the range of 10 raised to minus 4 or 5 decimals, right? So that kind of improvement accuracy we don't need. We need in the accuracy of 98, 99, 95.6, kind of like that, right? So we want in that range. So you have to understand when you are trying to train your model, see that after which point of time your model is not improving to a good extent. Now it is running perfectly fine, I guess. Again, it is showing, as I said earlier, from 2000, if we keep up to 3000, our training accuracy is still showing 98. Maybe it will be in the some decimals. So if I keep like this, it's, so like kind of 97.6, 97 point something, right? So even though I have increased the epoch by 1000, it is not improving my model as such. So I should understand that where the limit would be. So I just to give a I just need to find the optimal epochs by multiple trainings to identify that till what time I should stop, because this is small data. I can pretty much work with this because it has only 1000 points. But when you're getting a data points with which lakhs and billions of data, there the increase having epochs within this range is not an ideal situation. Okay, you might have epochs max to max into 10 to 20 in the tens of ranges, right? So you have to, because each epoch might take hours of time. So that is something you need to take care of like that. And it is 3000 epochs also not that much difference it is giving like this. So that is what I'm trying to explain it here, that even though whatever uh, network you're going to write, we just write the exactly the mathematical equation derivation of whatever we have seen in lecture as in the code. And we have seen here that after certain point of time the learning will not improve to that extent. There we need to stop. Okay, so here we are seeing the importance of epoch. uh, but if you want to, if you for same epoch, let's say 1000, if I keep the learning rate 0.5, let's see how it will run. You should not be writing this program in the actual production code, but you should know that you should practice it to get to know that whatever the equation you have seen in the derivation of a learning algorithm, how it is actually play out in the code, right? Because all these big classes that we have written, it will come down to few 5 to 10 lines. You don't need to write all this stuff. The reason, the purpose of writing all this stuff here is to make you understand that whatever the mathematical derivation that we have seen in the lectures, it is actually written in the code. And when you are going to use some library called PyTorch or TensorFlow, which we have to use maybe from next session or next to next session, I will introduce the TensorFlow concept here, TensorFlow, PyTorch, anyone I will pick, and I will show you that concept here. How to write all this code, maybe it's 100, 200 lines of code. You don't have to remember this, but just to get a proper intuition about it, like how you from derivation get an intuition about how things play out. From code also you should get intuition about how things actually playing out while learning a model. First, just for writing three neurons, we wrote 100 lines of code. Just imagine if we have a model of 5 6 hidden layers. In each hidden layers you might have maybe 10 neurons. That means approx 50 neurons are there, excluding input and output layer. So how much complex it will become, right? So that is something you need to appreciate, get understanding about it, and you start getting appreciated that this much complex things has been happening, and you're going to write only one line of code with respect to it. Okay, so once we introduce the learning rate, we have seen the loss function a loss value which was earlier 0.05. It is increased, it is now it's become between 0.25 to 3, and this lots of spikes are here in between. So if we run this also, we can find that again our value training accuracy come down to 0.73 and 0.72, and its learning was same. So the combination of epochs and learning rate also affect us. Can we get this program? Actually, I have shared this Google Colab notebook with all of you in the chat, so maybe anyone can again post it down here. Is all this code going to be with you people? Okay. Now, what I will do, let's since have we had last 10 minutes. Okay, what I'm going to do is the same thing that we have seen here as a code. I'm going to give you a generic code with that. I'm just going to have an overview with it and going to show you how it is going to run for multi-class classification. Now we have seen for binary classification how FeedForward network can help you with multi-class classification. Okay, to give overview that, let me show you the generic output layer. So let me see whether I can show you like this. Okay, So this is a typical general multi-classification feed-forward network. Okay. Now you might have layers. Okay. So there will be input layer called L0, then an output layer called NH1, NH plus 1. I will tell you what is NH plus 1. Then there is something called hidden layer. Okay, and each layer will have some N1 neurons, N2 neurons, kind of like that. Okay, so you will have n in x, you have n features. Okay, n dot x, some number of features you have. Now each input will be given to each of the n1 neurons in the layer 1, and each neuron will have its while passing it, each will have its weight, right? So and each neuron will have its bias. So if you can see B11 here, that means B1, first one is basically layer number 1, and one specify the number of which neuron we are talking about. So here B first layer first neuron, B12 is first layer second neuron. Similarly B1 first layer and one neuron. Like this is a whole terminology is there. Now for weight it will be like that. First number 1 it's going for layer 1, second number 1 is for basically first neuron, and the last number 1 it tells about the which input feature you're going to talk about. So if it's write as 111, it is like first layer first neuron and the first feature. If you write 112, it is like first layer first neuron second feature. Like that weights has been assigned. Once this weight has been assigned for first layer, you will go down to second layer, where the output of a H11 or H basically will be passed down along with weights and the biases to the second layer. Similarly, n number of layers will be there, H number of layers will be there, that's why it's n H layers. Okay, and at the end you might have, if you're having multi-class classification, you will have different classes, that is y1 y2 and y kind of thing, where you're going to apply softmax function. Softmax function is going to give the output within the range of 0 and 1 for different classes which equal to 1 only. So if you have 10 classes, so maybe for class 1 it will give you 0.01, and for class 2 it will give 0.3, and class 4 it will give 0.21, kind of like that, which equate to 1. So we are using softmax function for the classification only at the output layer. Before that, all the hidden layers we are using the simple sigmoid function as an activation function. Okay, so this is the general feed forward network that is something you're going to use. Till now we have seen 3 neurons. This is the actual scale up thing, where you can have h number of hidden layers, where you can have n number of neurons in each layer, where each layer might have different type of neurons, right? So how you can compute it, and at the end output layer, when you're trying to do a activation function, you're going to use softmax function. Okay, so this is a typical feed forward network. Let me get out of here and get back here. Okay, so this is the generalized scenario. So what we're going to do here is, I'll just basically copy paste the code here and simply run it. I will just go through it, what actually through is going to be look like. Okay, so I will just explain it better as a general class. So I am going to post all this code here in the one which we are doing, but for now let's just get a basic understanding of what we are trying to do. If it's looking complex, that's totally fine, you don't have to remember it, but whatever we have written as a code earlier, we just compressed it into a simple into using some function, right? So in initialize function, so we are giving few things. We are giving the number of inputs that we are having, that is x1 to xn, the number of input we are having. That input means in a data set how many features you have. So you might have 10 features, 20 features, 30 features, that inputs we are talking about. Okay, instances are different, each instance will have 30 features, 40 features, but here when we're saying inputs, we are talking about one feature at a time. Okay, so n inputs, let's say a data set has 30 features, so let's say 30. Now hidden size, it talks about the input layer in hidden layers. So it will, let's say if I write 2, that means I have a one hidden layer with 2 neurons. If I write 2 and 3, I have 2 hidden layers with first layer is 2 neurons and second layer is 3 neurons. If I write 2, 3, 5, then they will be third hidden layer with 5 neurons, like that. So we are initializing it. Now there's something called self sizes, which is going to calculate the amount of neurons overall we have in the feed forward neural network. Okay, then we are initializing them. We're using random function, and for bias we are giving them zeros. Okay, now we have function sigmoid function as it is. Then we have something called as forward pass. Now what forward pass is basically doing is the same thing that we have done here. This forward pass, that means we'll multiply the weight with its input feature, that is input x1, multiply the weight with input x2, and each neuron will have a bias, so we are going to pass this. So all this code that we have seen here, we compress that into the two line here, a and h here. So instead of b, we are writing as so a is a pre-activation function. We are multiplying w and we are multiplying the w and x here. We are writing as h, and we are giving b as a bias. Similarly, once the pre-activation is there, then we are calling the sigmoid function on the a pre-activation output that we are getting, that is from a. So this is something what we have written there as it is. We are writing in the more complex format and in a more scalable format. So this is a forward pass. Now for sigmoid function, we are returning the grad function. So this is there, and for basic grad function, where we are updating the value of w, weights, bias, h and a. Why h and a? Because now the scenario is like, so one layer as well as in each layer. So for that, we just wrote it down as a for loop directly, which we're going to calculate for each layer. For each neuron, we're going to calculate the WBHA. This is the formula we are finding it using it same thing what we have done earlier. If you're not able to understand this, you can check the way it has been derived. The same way we have written in a more compact format. That's nothing else we have done. Now once we have done this, we are calling the fit function, where epoch is 1, learning rate is 1, initialize is 2, initializing that there's w and b, and we are updating the w and b value all the time for each epoch. So once we get this value, we are calculating the display loss, and like what we have seen done earlier in the last two attempts, same thing we have done, and we are plotting them with respect to epoch and mean square error. And with respect to the predict function, we are for this happening here is we are passing now whatever that's a generalized feed forward network we have written, we are passing it here with two input features right now. Not as it's a, we are just passing as a binary classification as of now, and the input is 2 and 3, that is two hidden layers are there. In one first hidden layer there's 2 neurons, and second hidden layer there's a 3 neurons, and we are training it. So once we are training it with 1000 epochs and learning rate of 0.01, we are getting loss error, mean square error with respect to the less than 0.05. So which is giving us a training and validation accuracy of 0.97 and 0.94. So if we do this, it is showing us pretty good value with respect to the how it is plotting. So this is for binary classification. Okay, so we have done using generalized one, and we are showing this. We have seen that even the complex function. So what you have to observe here is, earlier we have only 3 neurons. Now we have here 5 neurons, maybe not 5, even 6 neurons. Output layer will have 1 neuron, hidden layers has total 5 neurons. Right? Even with 6 neurons, we are getting accuracy of 0.97 and 0.94, which we have achieved same with the 3 neurons as well. So again, I want to emphasize that the more complex you will make a network doesn't mean that it will improve the accuracy. So even though we have with 6 neurons, we are getting the same training accuracy and validation accuracy which we got from the normal 3 neuron feed forward network, right? That is one thing I want to emphasize with respect to this. Now we have the same class with respect to multi-class classification. Only difference what we are doing is that last function we are defining a softmax function. The output layer we are putting as a softmax function. Okay, this is one thing, and this another part will come into picture. So again we are extrain bytrain we are defining it, because now the labels here we have 4 labels. So what we are trying to achieve here is just a minute. Yeah, so ultimately we started off with this data, and we want to see that whether our feed forward neural network can identify this 4 clusters or not. This is what we want to achieve. That is the start with the goal we have want with. We started with the binary classification, but now we are going to multi-class classification, right? So this is what we want to achieve. Now the only difference what we have done, the function will be as it is. We have added softmax function at the output layer. That's the only thing we have done. And we have what we have done is one hot encoder. So what does it mean by that? Means when we say class 1, 4 classes that we want to classify our dots into, that is red, blue, green and all that, eventually the machine has to understand. So what we can do, we have to tell the machine that what class 0 represented as. So class 0 represented like 1 and other classes are 0. So when class 1, let's say red represented as in the second value, it will represent as 1, others are 0, like that. So we are trying to put it into a kind of list, right? A list or an array, whichever you want to we can say about. So we want to define that the output function, that is which is going to give me 4 values. From that 4 values I have to identify in which class it is belong to. Okay, that for that we are using one hot encoder where each class has been encoded differently. So the way we have shown it here, the one I am highlighting. Okay, so we're using one hot encoder when we try to train a model. So here what we are trying to give, input features are 2, the x1 x2, output is 4, that is we want 4 class, that's why it's 4 outputs, 4 classes there, that's why 4. We have 2 hidden layers with 2 neurons and 3 neurons respectively, and we are training this model on 2000 epochs with learning rate of 0.05. So once we run this, we get this kind of epochs versus loss function. Sorry, in this loss function also we have keep as cross entropy. Why cross entropy? Because for most of the multi-class classification, we instead of square loss function, we typically use cross entropy function. You can use mean square loss function also, that is totally fine. But typically, generally, it is observed that cross entropy is a good parameter for the multi-class classification. So once we did this, we get the accuracy 0.89. We can obviously improve it by reducing the learning rate or increasing the epoch. Now let's see the output. Now if you can see the output here, it has able to identify 4 classes, 4 clusters, obviously with certain errors, which we can see error in the terms of big dots, and the small dots show the actual correct classification of the data points, right? So this is something which is the feed forward of maybe 5 plus 4, 4, that is 9 neurons. With 9 neurons of feed forward network, we are able to achieve a complex function which can identify, which can divide the data points into 4 clusters, right? So this is what a capability of feed forward network is. As we go along with backpropagation, it will get more and more powerful. But by the end of this session, I want you to experience that with respect to coding, that all this big lines of codes and all that you have seen is directly taken from the mathematic derivation that you have find. You don't have to remember it. You can, but you should appreciate this, that whatever the function you're going to use, because next time I will show the same code with very less line of code, maybe 10 11 line of codes, and show that whole this thing can be done in few lines of code. Okay, but to appreciate that what is actually happening behind that functions when you're calling them, this is what the actual step process is going on. Okay, that's the first point. Second point is with respect to the multi-class function classification or binary classification, where the data is spread non-linearly like this. It's the few sigmoid neurons, even the like 3 sigmoid neurons. We have tried and tested with 3 sigmoid neurons, 6 sigmoid neurons and 9 sigmoid neurons. It can capture multiple relationship with respect to that. Okay, multiple complex relationship with respect to that. So that is something you need to start appreciating, that how it is started understanding the data, more and more complex data with very less number of neurons. Okay, so that is something from my side for today's thing. I will send you this code, and properly with the in the YouTube link itself. It will be there. So if you have any question with respect to it, please let me know in the chat section. So from my side, the class is over, and I'm going to give you this updated uh, sheet as of in maybe in half an hour. I will update it. Okay. Yeah, I'm going to share the same the same code that I have written earlier. I'm not able to recollect it, do it, so I've wrote it earlier. I just give you the same thing. That is totally fine from my side. Okay, so that is from my side. If you have any other question, please let me know. Yes, ma'am. Survana B. You can unmute yourself as well. The permission is given for unmute yourself. Also is given.
Hello, sir.
Yeah.
Can we run the same code with some modifications for other kind of activation functions?
Yes, yes, yes. You can totally do that. Actually, the code, whatever Sigmoid, the function softmax and all, we have hard coded it, right? But if you go to sklearn metrics or sklearn libraries, not sklearn metrics, sklearn libraries, you will find similar function. You just need to import that function, and that way you can use it. You can place it any other different kind of activation functions as well. That is totally fine.
Okay, so in sklearn library, there are already pre-installed functions for different kind of activation functions.
Yes, yes. Whatever we have done as of now, till this point, is just to show you how what actually happens the back. So maybe in the next session, I will show you the same code with very less line of code. I will just import the functions. We will do the same everything as it is, and we will see that the difference between that. Okay. So whatever the mathematical stuff we have written in the code is not something you need. We have to read about, but you have to appreciate it that that much processing is actually happening in the back. This much code actually written in the back, you're just getting a wrapper on top of it, which on which you're just calling a function.
Okay, so if any other kind of activation function which is not there in the sklearn, we can do it by ourselves
By you
in the
can exactly. So see
in
by
real life when we need some kind of activation function which is not there, we can hard code and use it in the similar fashion.
exactly. The reason is by the time, see, whatever the this mathematics that you getting right, it's coming from research, multiple research papers and all. So people will keep on tell about new and better activation function, but by the time it get more, but it will not reflected in the libraries such as sklearn or any other libraries, TensorFlow or PyTorch, because it takes time to get into production code. So that's why if you have some good activation function which you have read somewhere in a research paper or somewhere else, you can directly hard code it and then you can use it.
Okay, thank you, sir.
Yeah. So Survana B, I think you have some doubt as well.
Sir, good evening.
Yeah, good evening.
So, administrator, there we are having 28 by 28 it is. So, if you want to use, if you want uh, so how
I'm
many
sorry,
things are
your voice
there?
is getting disconnected. I'm not able to clearly hear it. Let me stop my camera once. Maybe yeah. Can you try one more time?
Sir, for fashion limited, is this 28?
Mm,
Want
so
if I want to create a particular for it, am I
sorry,
audible?
Sarvana, I'm not able to hear you clearly. It's better. Okay, I will wait. You can just keep typing it off. I will stop the recording in the meantime. Just can you please type it down there because I'm not able to hear your voice clearly. And I will stop the recording.